and I think I've already sort of referenced like derivatives relating to velocity, right? Like if you have a function, again, this is on page 34. So if you have a function that represents position, and that's where the like PVA. So if you have a function that represents position, its derivative, which would be like its instantaneous rate of change, could be thought of as velocity. And then the change of velocity could be thought of as acceleration. So and it's very basic though. It's very elementary. And in fact, our motion is going to be restricted to just like binary. Like so, notice it's like it's going to be moving along the x-axis. So we can either go right or left. We can go up or down, right? So and obviously we know that you if you had a free moving object, there are different components to your particle if it's moving or whatever. So for us, we just have to kind of take it very simply. So here's a velocity function, and I went ahead and already gave you what the acceleration is. So I already did like any kind of chain rules, any kind of product rules, any kind of simplification. So I've got a velocity and I've got an acceleration function, and I want to analyze the motion of this particle based on velocity acceleration from 0 to 10. And so it says draw a sign chart. And so I'm assuming at some point you've done sign charts before, and I gave you a lot more room than I have on mine here, so I'll have to fit this in. But like maybe like in one line called V of t from 0 to 10, and then like right underneath it do like A of t from 0 to 10. And we want to put down the zeros. So notice that like for the velocity, there would be two critical values, right? 2 times when the velocity is 0. Those are so 2 and 4. So I kind of want to indicate like, well, here's time equals 2 and time equals 4. And then what was the acceleration critical values? 2 and 10/3. And 10/3, is that bigger or smaller than 4? Smaller. So it'd be before, like if I'm trying to line everything up, like maybe there's 10/3. Okay. So let's keep track. Again, if I'm on the x-axis, a positive velocity I'm going to associate with moving to the right versus a negative velocity moving to the left. Right. So as I start looking at these intervals, let's kind of keep track. Is it positive or is it negative? And so you could just pick a representative and kind of just analyze the sign of it, or how like I know there's lots of different ways to analyze sign charts. But like if I pick, let's say 5, I know that's going to be positive, and that's always positive. So I know 5 was represented over here. So anything that's over here would have a positive velocity. And I'm just putting pluses here. Doesn't really matter how many you put. That whole interval is positive, moving to the right. And then between 2 and 4, what kind of velocity do we have? Negative, right? Because let's say you pick a representative 3, that's going to flip that to being negative, but that's still positive. And what kind of velocity do we have between 0 and 2? Negative. Still negative, yeah. And one thing that when I teach sign charts, I like to talk about the multiplicity of the roots. Like 2 had a square term into it. So the behavior on either side is going to match. It's going to balance. So how is this possible? How could I have negative velocity, 0, and then negative velocity? Like what describe that motion. What's happening? Yeah, exactly. Right. You move to the left, pause, move to the left. All right, and then move to the right. Okay. So that's my sign chart for velocity. And same thing we can do for acceleration. Like pick a representative and find out when is the acceleration positive, when is it negative. And notice if we're going to use that multiplicity, they're all odd factors, so these are just going to alternate, right? They'll always switch signs, which is nice. So, and it's a positive function, and it's quadratic, so like it's going to be positive, negative, positive. If you see that that pattern, or just take a representative and you type that in. plug it in. So it's positive here, it's negative here, and it's positive here. Does acceleration tell you if you're speeding up or slowing down? Does acceleration tell you if you're speeding up or slowing down? And Abram is shaking his head no.
Tells you the direction, because you can like have it could be negative and you can still be speeding up, but you're just speeding up in the negative direction.
Exactly. Acceleration by itself will not tell you if you're speeding up or slowing down because of the direction, right? So we need to look at both the acceleration and the velocity. So in the direction, you're right on the mark, Abram, right? Because I could have a negative acceleration, but if I'm moving to the left, that means I'm getting my velocity in that direction is increasing over time. So I'm actually speeding up to the left. So anytime the signs match, you're speeding up. So that's why I like to line up the sign charts. So like right here, if I highlight like this part from 0 to 2, right? 0 to 2, I have negative velocity and positive acceleration. So what am I doing? Negative velocity and positive acceleration.
You're moving to the left, but slowing down.
Yeah. I'm moving to the left, but slowing down. That makes sense, because at t equals 2, I better stop momentarily, right? And then I'm still moving to the left because my velocity is still negative, but I have negative acceleration, so I'm trying to speed up to the left. Right, very good. So this, anytime they don't match, they're slowing down. Anytime they match, they're speeding up. Anytime they don't match, they're slowing down. So I actually have a thin little spot right here that's also slowing down. Okay, so then where does 2.5 land? 2.5 lands right here. So you take a look at the signs. They're both negative. So I'm speeding up. And I mean, this is a really common question. They love asking this on the AP exam. Now, they might give you other functions that aren't as simple as this. But if it asks you, is it speeding up, slowing down, or stopped, justify your answer. It's the same no matter what functions you are. You have to compare velocity and acceleration. So I would say, oh, it's speeding up. How do I know? I could say v of 2.5 and a of 2.5 are same signs, or are both negative. Okay. Does that make sense? Yeah. Cool. So then how many times does a particle change directions? Not including 0 and 10, because those are in, right? But within the open interval, how many times do we change directions? Ella? Yeah, just one. When?
At time equals 4.
Yeah, perfect. Right? Because don't be confused at time equals 2. It could be like I could be stopping here and saying, well, hello, Emma, and then keep going. I didn't change directions. Like I say hi to Nick, who's not Alec, and then I can turn back and say, oh, Louise, I hope you're having a good day. Right? So just once, at 4. Oops, 1, yeah, is that t equals 4. Okay. And then are there any times when they were slowing down to the right? Any times we're slowing to the right? What do you think? Slowing to the right? I don't think so, because you'd have to have positive velocity to move to the right, but to slow, we'd have to have negative acceleration. So I'm just going to keep on going to the right and out the door. Faster, faster, faster. There are none. Okay, so I just wanted to use that as kind of like an introduction of hey, here are two functions. Let's analyze their motion. Now, how many people have studied position versus time graphs before? Just curious. Show of hands. Position versus time. How many people have studied velocity versus time? Probably the same number. Okay. So here's what I'd like you to do. See what you remember. Okay. I'm out of Kleenexes. I know. Like, is that what you're looking for?
Yeah.
Yeah. I might have some in the closet, but give me a second. See what you remember in example 2. See what you remember in example 3. analyzing a position versus time and a velocity versus time. And have a conversation in your group in case maybe some of you forgot. I will look for the cleaning. Thank you. See what you remember. And again, maybe if you've got a really strong physics background, this might be super duper easy. But if you don't, then it might be a challenge.
No,
I have a napkin. Josh, is that okay? I mean, it's better than your sleeve.
I'll take it.
Yeah. To change directions, you physically have to go from right to left. Not stop to left. Or stop to right. Okay. The same.
I don't know if this counts as change direction.
I'll give you the answer to A. 2. Just 2. Right? Because think about this. If this is your position for the first 2 units of time, your position hasn't changed. I'm just staying here for 2 seconds. And then I go to the left. Right? Because I'm going down. And then I go to the right. Okay, so if you're wondering about that, you're only changing from there and there. Those are your 2 times. Oh wait, sorry. It's 2 times, but I circled the wrong ones. It's a position graph. My bad. How about there? You should, right? Because this is right. Isn't this position graph? Yes. Whew. Right. These are all the positive positions. These are all the positive lines. Right. These are all the negative. So I switched from like here my position was 2, 2, 1, 0. Ah. Oh no. Oh yeah. No, I was right the first time. Oh my gosh, I need lunch. That's what I need. That's my bad. Sorry about that. Oh, that's if it were a blast. Thank you. Yeah, I need lunch. I need lunch. I mean, I could have played off as I'm trying to trick you, but I wasn't even trying to trick you. I literally haven't eaten anything since breakfast, so I need to eat next day.
Does it end up where it stops? Velocity is
No, did I give a I gave inches, right? Okay, so inches first. So if this is truly a position graph, velocity is the derivative. So I'm looking for slopes. So that's why I have the next 2 in green. Moving to the left means I need a negative velocity. So I'm looking for negative slopes. And then what is the velocity specifically at 3? I can just read the slope since it's a linear function. What's the acceleration at? Well, actually, that's a okay. It doesn't really matter. Can we? I don't like this cusp here because I don't like that there's no derivative that exists there. Let's change this to 3 to match this. What's the acceleration at 3? Like right there. What's the acceleration there? If this is the 0? How come?
Because the velocity isn't changing.
It's constant velocity. The velocity is constantly -2. So then the derivative of -2 is 0. Yeah, so, and in fact, it could have been anywhere here, right? Anywhere here, its acceleration would be 0 because I'm constantly going a velocity of -2. Now, this is where we leave the world of physics. Because the world of physics describes like our surroundings, like our life. But math doesn't have to. Because all of a sudden, I went from -2 velocity to 2 velocity, right? So now we're entering kind of like the world of Harry Potter, where we can just kind of like apparate from here to there, right? Teleport. So this is where we leave physics. Like if this truly represented a particle moving or someone walking or whatever, it would have to change gradually, right? You have to have more of a smoother transition. So just take that with a grain of salt. Okay, so it is 0. And I probably should label, like it's 0 inches per second, or 0 inches per second squared. Just know and remember those acceleration formulas. Okay. Average velocity of the object over the 10-second interval versus average speed. What do you think? Average velocity versus average speed. What do you think, Aro?
It's the velocity is -0.2.
Say it a little bit louder.
Like -0.2.
Negative 0.2. How'd you get that?
Look at the starting, I think, kind of graph.
Okay.
And then you find like the slope of the entire thing.
So the average velocity would be like the velocity of 10 minus the velocity of 0 all over 10 minus 0. Right? Okay, and then what was the velocity at 10?
Velocity of 10.
Well, assuming that, like, they kept going, right?
Yeah.
Did you say it? I didn't hear you.
No, I didn't.
Oh, okay.
I'm trying to figure it out.
Someone help him out. What's the velocity of that?
-4/3.
Change of 4, down 4 over 3, right? Negative 4/3, okay? Minus initial velocity, assuming that it kept going the other way. 0. All over 10 minus 0. So what is that? Negative 4/3 over 10, so negative 4/30ths? No, I don't know if that's what you said. Divided by 2. So what is that? Negative 2/15ths? Different color. And that's what, meters per second? No, inches per second. So average velocity. Now, average velocity can have a negative value, just like velocity can, just like acceleration can, because they're both vectors. What about average speed? Emma.
Speed doesn't have direction. So
Okay.
it would be 2/15.
Speed doesn't have direction, which is correct. It doesn't necessarily mean, though, that we positive 2/15. It might. It depends on if we spent more time going in the positive direction or the negative direction. But she's absolutely right. Speed does not have a sign to it. Ara, what were you going to say?
That's what I'm saying.
Average speed, here's what I like, Emma, what you said. And you might be right, I have no idea, because I haven't done this problem yet. Average speed would represent the total distance over time. Right? Ooh. I may have answered the first part wrong for part E. Because I may have wanted to do displacement over time. Right? I think that's what I wanted to do. Yeah, because Emma's making me think about this total distance over time. Let's do speed first. All right? I think I found the average rate of change of velocity, which actually is an acceleration value, because it's a change of velocity over time. That's actually the average acceleration. Boy, Mr. Brown, you're so advanced. Let's fix this. See, this is what I get when I don't eat lunch. Average velocity is displacement over time. So it's still going to be over 10 seconds. But let's think about displacement. Oh, Ara, I think you're absolutely right. Did you say negative 0.2?
Yeah.
That's where that came from, right?
Yeah.
Right, because your initial position was at 2, and your final position is at
0.
0. So you have from 2 to 0, you went back 2. Final position minus starting position over time. There it is. Oh my goodness. -1/5. Let's do our average speed. That's distance over time. So direction doesn't matter. That's exactly what Emma said. Emma, good thing you said that to get me on the right track. So we need to keep track of how far this is traveling. So we start at position 2, and we go all the way down to position -2. So we traveled 4. And then from position -2, we travel all the way up to position 4. So we've traveled, 6 more? So 4, right here's your initial 4. And then we've traveled up here, so 6 more, that's 10. And then we travel 4 more this way, which is 14. So our total distance is 14 inches over 10 seconds, or 1.4, or 7 over 5. Think about that. They're both labeled inches per second, inches per second. And Emma, I'm glad you like what you had said made me think about this, because very rarely will these be opposites each other, right? It just depends on how long and how quickly you're moving from the right to left. I really hope I did not confuse you. I'm so sorry. Can you forgive me? Please? Navika, please. I'll write you an extra really good letter.
Yes.
Okay. Do the same thing with the velocity graph. Okay. I believe it's the same questions, but just now we're looking velocity versus time. Oh, yes. Page 37. Page 37, there's also a summary of what we are doing right now. So if you look at page 37, I promise you I got it right there. I go through everything when it talks about position versus velocity. Phew. Okay, but yeah, so in case you're a little rusty doing the homework tonight, or I really confused you, you're just too nice. 37 is a good reference. But let's finish up on page 34 with our third example. Once you do that, then you have time to look at homework or things like that. I never remember what time this period is. Oh, we still have a lot of time, 36. Good. So let's go through this velocity graph.
Oh, true. Like bounce off the line.
I'm really nervous to ask this. Do these look okay? Right? Okay. Yeah. So velocity, when does your velocity change signs? So you cross the x-axis, because these are all positive velocities, these are all negative. And then when it's below it, that's how you know you're moving to the left. And again, thinking about the slope, since that's acceleration, if I've got a negative slope and I have a negative velocity, it just means I'm moving to the left much quicker. Here I'm moving to the left much slower, right? So I start to eventually get back up to 0. And that's going to help me answer D. Is it speeding up, slowing down, or stopped at 3.5? So finding 3.5, so 1, 2, 3, so that's like right there. What is it? Is it speeding up, slowing down, or stopped? Speeding up, right? Both velocity and acceleration are negative. So I could just justify it's speeding up. I could say A of t and v of t are both negative at t equals 3.5. Or you can actually even say what the values are. What's happening at 7.5? Speeding up or slowing down? Slowing down. Just curious, what direction is it slowing down? Towards the right, towards the positive? Where do you look for that?
It's because the velocity is positive.
Because it's right, because it exists above the x-axis?
Yeah.
Yeah, with a negative slope.
Yeah.
Perfect. So it's slowing down. So you could say v of 7.5 is positive, but a of 7.5 is negative. And that's a perfect justification. And I love using like the battery signs. I don't know if that's what they're called, but like if I want to say the word positive, I just like to put a little plus with a circle around it. Positive or negative. Negative. So I like that. Ooh. Now I know at least one person in this room knows this because I had a conversation specifically with this person. Is it possible to find distance traveled when you're analyzing a velocity graph? And maybe lots of people know this, but at least one does for sure. Is it possible? Yes, Emilio.
I think if you find the area under the graph.
Yeah. Yeah, if you look at the area under a velocity graph. And the reason that this, and that's kind of like, it's kind of like alluding to like one of the fundamental theorems of calculus. But if you just look at a constant velocity, like if I'm constantly going 60 miles per hour, like, if I'm going 60 miles per hour for 3 hours straight, 1 hour, 2 hours, 3 hours. So if I have 3 hours and I'm going, like it's a velocity graph, so 60 miles per hour times the hours, like the hours sort of cancel, like from just a unit analysis. And I get, 60 times 3 is 180 miles. I know I'm 180 miles away. And that's what this, that's sort of what this region represents, this area under the curve. So the answer is yes, you can find distance when you look at area under the curve. So I don't think I'm really supposed to tell you this yet, but I do, so too bad. Just don't tell the AP board yet, right? And since velocity does have a sign, right, since it's a vector quantity, if that area is underneath, like that could be referring to the distance moving to the left versus the distance moving to the right if it's positive. And if it's total distance, you make them both positive, but if it's displacement, you start to balance out. Like a sine graph, right? If my velocity is perfectly represented by a sine wave, and not the negative sine wave, but the sine wave, right? And I think about, the distance traveled will be this area. And so if I went like 2 pi units of time, my displacement would be 0 because I have the exact area on the top and the bottom. But if I wanted my total distance, I'd have to figure out what 1 is and then double it, right? And do you know, this is so cool. Do you know how much area is here? Do you know? From 0 to pi. You know how much area is there? This is just stuff that I, random do. This is really cool. I'll tell you what it is. We'll prove it next semester. End of the semester. What's that? Yeah, you probably did this. This is so cool. This is like this has 2 sides. There's a sine curve and a straight line from 0 to pi. It's exactly 2. That region is exactly 2. that crazy? All right, anyway, that's all. Okay, so this is page 37, is a summary. And I think is it just one sheet or is it two-sided? Oh, it's front and back, but they go pretty quick. So yeah, sorry. Well, it's only two problems, A through L. There's only two problems. Okay, and we have about 15 minutes, so or maybe 10 minutes. So what you can do? That was fun. That's really cool. That is exactly two.